Hey guys, welcome to the aircraft structural mechanics class. So in unit 1 we are going to see structures in aircraft. So the topic number 4 we are going to see airframe, right? The purpose of this course is to teach the principles of solids and structural mechanics that can be used to design and analyze aircraft structure or aerospace structure, especially the fixed wing component like aircraft. So here we have different type of the flying machines. One is the flapping wing and the fixed wing and the glider we have, and the different the paraglider modeling, which is have high aerodynamics models. So these are the different type of structures we are going to analyze, and we are going to understand how the airframes are there, especially the fixed wing aircraft, how the fuselage is designed, how the wings are designed, and engines mounted in different locations like wing mounted engine, fuselage mounted engines, and the empennage mounted engines are there. So these are the different structural elements which have different airframe models, as well as it has to be lightweight in design, as well as it has to be less drag producing element, like we have to concentrate on aerodynamics also. So airframe, let us go for the fixed wing aircraft. In this picture, we are understand that the fuselage is there, where fuselage bulkhead is there, longerons is there, stingers are there. Fixed wing, we have it is a tapered wing, low wing configuration, and the engines are mounted in the fuselage, and tail, this empennage is high wing tail, this is horizontal stabilizer and vertical stabilizer. All the structural members or airframe members have the longerons, stingers, stress, right? So the function of the aircraft structures, we are going to see the major element like spar cups, spar webs, skin, longerons, stingers, and transfer nibs are there. In structure, most of the flight vehicles are thin wall structure, usually to transfer the shear force, and the major stingers will carry the bending and compressive forces. So to resist the applied load, aerodynamics loads acting on the wing will be based on what shape we are using, how it designed. So to protect the connection in the environment, we have to be designed properly, both in structure as well as the aerodynamics. So now coming to the definitions of primary structure and the secondary structure. In the critical load bearing structure on the aircraft, if this structure is severely damaged, the aircraft cannot fly. Like if the engine is damaged, if the wings are damaged, then this is the primary structure. If it is affected or if it will get failed, so the entire mission will fail. So we will call this kind of structure, we call it as a primary structure. Whereas a secondary structure is the structural element mainly to provide enhance the aerodynamics, like fairing to, for instance, for found where the wing meets the bodies or at various locations on the leading edge or tailing edge of the wings. So we have flaps is there, control surface are there, trim tabs are there. These are the additional members where it will operate or it will be work even though it get fails. So these are the secondary structure. Even this secondary members or secondary structure get fail, the mission will not be fail. So up to the safe region, it can be able to fly. So now we are coming to the different structure. As I said, we have monocoque structure we have. So unstiffened shield or shells, we call it as the monocoque structure. Fuselage we usually use as the monocoque structure. It will be the relatively thick to resist bending, compressive as well as the torsion load. We have the major three loads. One is bending load. It has to be resist bending. It has to be resist the compressive and the torsion load. So for that reason, we are using the monocoque structure. Next, we're going to see about the semi-monocoque structure. The construction with stiffening member, where the stiffness will be there in the semi-monocoque structure. It is also to require to diffuse concentrated load into the cover on the or the fuselage or the wings structure. It has the more efficient structure which could permit to thin covering the shells or the fuselage, This is the one example where the longerons or stringers will be attached to resist the bending, compression as well as the torsion. So, so we will see this picture. We have two things. One is fuselage, another one is wing. The construction of fuselage, the construction of wing represent the semi-monocoque structure. Where the semi-monocoque structure we have the stiffening element like longitudinal stringers, transfer frames, cover skins, spar, and the longitudinal stringers. These are the member which gives more stiffness and more strength to the fuselage and the wing. So this is the wing layout where all the control components involved like flaps, aileron, wing tips, leading edge flap, and the spars, wing root, wing tip, and inside we have rear ribs, wing tips, nose ribs, wing spars, rear spars, where we have the wing tank, the fuel tank will be there, and the wing roots. This is the wing layout where all the structure elements we are representing. Next, the function of aircraft structures. We'll see the different structures. First, we'll go with the skin. The reacts the applied torsion shear force transmitted aerodynamic forces to the longitudinal and transfer supporting members. Acts with the longitudinal member in resisting the applied bending and axial loads. So this skin will take torsion shear load while the aerodynamic forces are acting either in a longitudinal direction or the transfer direction in the member, like fuselage and the uh, fuselage and the wings. So it has transfer member is reacting the hoops and circumference stresses. The load will be structure take place as in a pressure value. So this pressure loads will transfer to all the members from the skin to longeron, skin to ribs, skin to ailerons, all the control surfaces. This skin will helps to transmit the torsion and the shear loads from the aerodynamic forces. Thus, now we are going to the function of aircraft structure in the specific part. One is ribs and frame, where the structural integration of the wing and fuselage involved and the keeping the wing in aerodynamic profile without collapsing or without changing the shape of the structure. So now we are going to the another part, spar, the resisting bending and axial load from the wing box for stable torsion resistance. So this spar will take place, the torsion load which will be resisting the torsion load and the bending as well as axial loads. Now stiffeners and the stingers, it resists the bending and axial load along with the skin and divide the skin into small planes, thereby it increasing the buckling and the failing stresses, which also increase the resisting load capacity of the axle due to the axial load caused by the external pressure. This is a simplification of the element, like it is called as a structure idealization. Due to the axial stress to the idealized structure, the behavior of this structure element is often idealized to simplifying the analysis of the assembled component. Several longitudinal may be lumped into single effectiveness, and longitudinal should be shortened computation. The webs carry only shearing stress, and the longitudinal members carries only axial stress. The transfer frames and ribs are rigid within their own plane, so the rest across the section is maintained unchanged during the loading. So here the simplification from the axial stress to the structure to the ideal structure, the webs will carry the shear load and the longitudinal member carries the axial load. So here we have the recalling the session, what is called a spar, what is called the stinger, what is meant by the shear flow on the shear center. So we'll see the next topic on the next class. Thank you.